Good day, this is Professor Will, CBMD PhD. Today is Monday, March 30th, 2020. It is 12:11, 40 seconds a.m. Eastern Standard Time. And today's lecture is going to be on cosmology, taking a little bit of a break from Corona. So let's get started here.
If the universe is only 10 billion years old, why isn't the most distant object we can see 5 billion light years away? This question makes some hidden assumptions about space and time, which are not consistent with all definitions of distance and time. One assumes that all the galaxies left from a single point at the Big Bang, and the most distant one traveled away from us for half the age of the universe, at almost the speed of light, and then emitted light which came back to us at the speed of light. By assuming constant velocities, we must ignore gravity, so this would only happen in a nearly empty universe. In the empty universe, one of many possible definitions for distance does agree with the assumptions in this question. The angular size distance, and it does reach a maximum value of the speed of light times 1/2 the age of the universe. If the universe is only 10 billion years old, how can we see objects that are now 30 billion light years away? When talking about the distance of a moving object, we mean the spatial separation now, with the positions of both objects specified at the current time. In an expanding universe, this distance now is larger than the speed of light, times the light travel time due to the increase of separations between objects as the universe expands. This is not due to any change in the units of space and time, but just caused by things being farther apart now than they used to be. What is the distance now to the most distant thing we can see? Let's take the age of the universe to be 10 billion years. In that time, light travels 10 billion light years. And some people stop here, but the distance has grown since the light traveled. The average time when the light was traveling was 5 billion years ago. If the universe does not have a critical density, then the distance is different. And for the low densities that are most likely, the distance now to the most distant object we can see is bigger than 3 times the speed of light times the age of the universe. How can the oldest stars in the universe be older than the universe? Of course, the universe has to be older than the oldest stars in it. So this question basically asks, which estimate is wrong? The age of the universe, the age of the oldest stars, both. The age of the universe is determined from its expansion rate, the Hubble constant, which is the ratio of the radial velocity of the distant galaxy to its distance. The radial velocity is easy to measure, but the distances are not. Thus, there is currently a 15% uncertainty in the Hubble constant. Determining the age of the oldest stars requires a knowledge of their luminosity, which depends on their distance. This leads to a 25% uncertainty in the ages of the oldest stars, due to the difficulty in determining distances. Thus, the discrepancy between the age of the oldest things in the universe and the age inferred from the expansion rate is within the current margin of error. In fact, in 1997, improved distances from the Hipparcos satellite suggested that this discrepancy has vanished. Can objects move away from us faster than the speed of light? Again, this is a question that depends on which of the many distance definitions one uses. However, if we assume that the distance of an object at time t is the distance to the object measured by a set of observers moving with the expansion of the universe, and all making their observations when they see the universe as having age t, then the velocity change in d per change in t can definitely be larger than the speed of light. This is not a contradiction of special relativity, because the distance is not the same as the spatial distance used in SR, and the age of the universe is not the same as the time used in SR. What is the redshift? The redshift of an object is the amount by which the spectral lines in the source are shifted to the red. That is, the wavelengths get longer. Are quasars really at the large distances indicated by their redshifts? Yes. Stockton, 1978, observed faint galaxies near in the sky to bright quasars at moderate redshifts. He chose quasars with moderate redshifts, so he would still be able to see galaxies at the redshift of the quasar. He found that a good fraction of the redshifts of the faint galaxies agreed with the redshifts of the quasars. In other words, quasars are associated with galaxies that have the same redshift as the quasar and have just the brightness expected if the quasars are at their cosmological distances. Thus, at least some quasars are at the distance indicated by their redshifts, and this includes some of the most luminous quasars, for example 2C273. Thus the simple answer selected by Occam's razor is that all quasars are at the distances indicated by their redshifts. What about objects with discordant redshifts, like Stephan's quintet? One famous example of objects with different redshifts appearing in the same part of the sky is Stephan's quintet. But the low redshift galaxy in the lower left is obviously more resolved into stars and looks bumpier. By the surface brightness fluctuation method of distance determination, this bumpiness means that the low redshift galaxy is indeed much closer to us than the other four members of the quintet.
Good day, this is Professor Will, CVMD PhD, on cosmology and astrophysics. Well, hope you enjoyed listening and have a great day.